we'll try to do a few more examples so that it becomes more clearer to you. So yesterday, and the first thing that you should remember in a block diagram reduction is that there can be multiple ways of doing a block diagram reduction. Okay, so not necessarily that everyone has to follow the same steps in order to get the final block diagram. So in the previous class, we had done one way of done the block diagram reduction of the same block, but in a different way. So in this class, let's see how we can do it in an alternate way also. So here what we can do is that, so this is a takeoff point that we have over here. So what you can do is that you can move this takeoff point ahead of, or rather after this block G3. So removing this takeoff point after the block G3, what will it do? It will result in that, so you will have to add this H1. So you will have to add gain, which is equals to 1 by the reciprocal of the gain beyond which you are moving the takeoff point. So that means you have to divide, you have to multiply with a gain of 1 by G3 to the already to the gain which is already there. So that means previously it was H1. Now if you move this takeoff point to this point, then this you have to change this block, the transfer function of this block. It will become H1 by G3. So this is done because so that the overall output of the system remains unchanged. Right. So the moment you change it over here, so that means now you see that you have a negative feedback loop over here. Right. So you can replace this negative feedback loop with this G2 G3 by 1 plus G2 G3 into H2. So now this becomes, you can represent this whole thing as a single block which is given, whose transfer function is given by this. So now you represent the same thing. So you have G1 over here, these three blocks, this thing has been represented or has been simplified by this one single block. Now here, and the rest of the blocks remains the same. Now here again you see that G1, this block, and this H1 by G3, this again forms another so here it's a positive feedback loop. So it's a positive feedback loop means here again you can write the overall the equivalent transfer function of this part of the loop. So that will give you an expression like this. So now you will have an error detector over here. This whole part will be replaced by this transfer function, which is nothing but this. And then this whole thing is basically another. Now this whole thing is another negative feedback loop. So what you can do is that from this negative feedback loop, you can write the transfer function and this will give you. So this is your end result where you are representing the complicated block diagram which was given to you by a single block, and this is the transfer function of your system. Right. So the methods or the reduction rules which are there. So did you go through it, or did you find any difficulty in understanding those?
No, ma'am, no difficulty.
Okay. So let's try solving this block diagram. So can you tell me the steps which you might want to follow in order to do the reduction of this block diagram?
Ma'am, first we can create G1 and G2 into a single block, and we can find a gain of G3 and G4 and again create a single block there.
So your G1 and G2 single block will be?
Yes, ma'am.
What will be the transfer function of that block if you combine these two? Can you repeat?
Ma'am, it will be G1, G2, ma'am.
Yeah, it is G1, G2. Fine. And then what about this G3? Again, repeat.
Then again we can find it for G1, G2 and H1, ma'am.
Yeah, so you can find, so this will become one loop and you can find the corresponding transfer function. So this one will be?
G1, G2 by 1 plus H1, G1, G2.
H1, G1, G2. Okay, so this part is been replaced by this one block. Okay, then
Ma'am, we can in near G3 and G4 there is a adder, ma'am. That summing point we can keep it after G5, ma'am, for our convenience.
You want to keep, you want to transfer this one after here.
Yes, ma'am, the +1 after G5.
But how will you, first of all, how will you take this? Because there are 2 points, na? There is one summing point over here, there is one takeoff point over here. So you have to move everything, like 2 things ahead or after this G5. But you can move like it's better to move only 1 point at a time. Like either you move only the summing point or you move the only the takeoff point. Here you have 2 things. Now you have one summing point over here and you have one takeoff point. So if you move this whole thing, so you have to move it ahead of this takeoff point and then again move it ahead after G5. So here what you can do is that you see that you have G3 and G4, they are just being added over here. So you can represent this G3 and G4, you can just represent it as G3 plus G4. Isn't it?
Yes, ma'am.
So if you represent this as G3 plus G4, so now you will have only one block over here. So 1, 2, 3, these 3 are changed by G3 plus G4. So now you have RS over here. You have this thing G1, G2 divided by 1 plus G1, G2, H1. Then you have so this is what you have now, right?
Ma'am, H2, ma'am.
Oh, sorry. H2, yeah. So this is what you have right now. So now then.
Ma'am, the H2 takeoff point, we can keep it after G5.
Yes, you can remove this takeoff point after G5. If you remove this, then what will happen here?
Ma'am, it will become H2 by G5.
Yeah, it will. Now this one will be replaced by H2 by G5. Good. So now this point has moved here. Then.
Ma'am, now the G3, G4, G5 and H3 we can replace it, ma'am, by its transfer function.
Yes, now this part you can replace. This is a negative feedback loop. This one will become
G5 into G3 plus G4.
G3 plus G4.
Divided by 1 plus H3 G5 G3 plus G4.
Yes. So now this block has been represented by this one. So then you have one block over here, second block over here, and you have a feedback H2 by G5. And this is a negative feedback, and then again you can find what is the overall transfer function. So then you will get RS, you will get some transfer function and YS. What will be the value of that? Or I think it's okay, you can find. So this is like the steps what you have already told. So first G1 and G2, then represent this, then combine G3 and G4, then move this takeoff point over here, and then finally you will end up with the final transfer function. Okay, so now let's see. So similarly, you can have multiple block diagrams and you can do the reduction. So this is like I don't know in that you can check later on in that Nagrath Gopal book or whether you have pages related to this block diagram reduction examples or not. So it would be better if you can do a few block diagram reduction. I have already provided some practice problems. So you try to solve those. So this is one. So this is the block diagram which we had drawn for that 2-tank liquid level system. So here again the process, the steps are given. So here what is given is that first of all they are moving both points. So this takeoff point, they are moving from here to here, as well as they are moving this summing point to here. So they are doing both the things at the same time. If you are not confident with doing both the changes at the same time, you can do it one at a time. You can first change, you can first take this, move this takeoff point after 1 by R2, then then give the write the gain in the corresponding path, and then in the next step you can move this summing point ahead of this one, and then again do like this is sort of they have done a step jump. So instead of doing that, you can do one step at a time also. Okay, and then now once you have this, so you have two loops, so you can represent like this, and this will be the final transfer function. So these are practice this block diagram reductions, and then if you have any problem, then we can always discuss in the next class. So is that okay, or do you want to signal flow graph. Okay, so these are like node number 1, 2, 3 and 4. So there are 4 nodes in the system. Okay, so now let's say that this node 1 is represented, so R represents this node 1, this is E, this is something D and this is C, and there is a feedback between node 3 and node 2. Okay, so basically, so here and this the connections between two nodes, that is basically known as the branch. So branch is the signal travels along the branch from one node to another node, and while traveling what happens is that the signal gets multiplied by the gain or transmittance of the branch. So if this is a branch, so and all the branches will be associated with an arrow, and that arrow basically it determines the direction of flow of the signal. Okay, so and each branch is given by the is represented by its corresponding gain. So now, so this gain is basically the gain or the transfer function that we were, in case of block diagram, we were representing in each block, we were providing the transfer function of that corresponding element, and here as an equivalent you can say that here between the gain of this branch, that will be equal to the transfer function of a corresponding block. Okay, so now let us say that, and the gains are given by this value. So let's say that this gain is G, this gain is 1 and this gain is H. So now if you consider this node E, so node, or rather let's say node 2. So you see that in node 2 there are 2 incoming signals. So 2 signals are, 2 branches are coming in and 1 branch is going out. Now if you want to find out what is the value of the system variable or the value of the variable at node 2, then what you do is that you just simply add the so this is minus H, let's say, since it's a feedback. So you just add the 2 incoming signals. So the system variable, or yeah, system variable at node 2 will be given by this, the signal which is coming in, which is nothing but R multiplied by the gain, which that is R multiplied by 1 plus this signal which is coming in. So this signal is coming from D multiplied by this gain, which is minus H. So D multiplied by minus H. So you will have R minus D into H. And here we are not considering whatever is the outgoing signal. So the system variable at each node, that consists of only equal to sum of all the incoming signals. Similarly, let's say so you can have a node which can be which can act as a summing point, it can act as a transmitting point, it can be a mixed node, different kinds. So here let's say again you have a connection of, so you have multiple nodes. So you have node number 1, 2, 3, 4, 5 and 6. So there are 6 nodes in this graph. Okay, and between each nodes there is a specific path, and the direction of the flow of the signal, that is also provided along with each branch. Okay, so now if you want to find out what is the value of this node value of the variable at node x1, so that will be equals to, so there are 3 incoming signals. So one is coming from here, one is coming from x2, one from x3 and another from x4, and x5 and x6, they are actually outgoing signals, so we are not interested with that right now. So if you want to represent this node as a summing point, so then you can write that the value of x1 will be equals to the other node variable x2 multiplied by the gain of that corresponding branch. So that means x2 multiplied by a21, then plus x3 multiplied by this gain a31 plus x4 multiplied by this gain a41. Okay, so this is so summation of all the incoming signals. If you have a node which has only that means this node is acting as a summing point. Then this node can also act as a transmitting point. So transmitting point means it is transmitting or there are outgoing signals from this node. So once when we are dealing with outgoing signals, so in that case you will write that x5, the value of x5 will be this x1, so this node x1, and the gain of the corresponding branch, which is equals to A15. Similarly, the value of x6 will be equals to x1 multiplied by A16. Now, if you have like other branches coming out or going out or coming in into this x5 and x6, correspondingly you will have to add those also in order to find out what is the value of the at that node. Okay, and usually the notation of is given in such a way that so the gain is written in such a way that Aij is basically the transmittance or gain of the branch, and it is directed from node xi to node xj. So if this is your node xi and this is your node xj, and let's say the signal direction is this, so then Aij will be the transmittance or gain of the corresponding branch. Now in a signal flow graph there can be, so a node can be, you can say that a node is an input node or a source node if the node only has outgoing branches. So if your branch, if your node has, so let's say like this is another signal flow graph. So you have 1, 2, 3, 4 nodes, and you have 1 branch, 2, 3, and 4 branches in this signal flow graph. Okay. So now here you see that if you consider this node y1, so y1 has only outgoing branches. So there is no incoming branches to this y1 node. So that kind of node which has only outgoing branches, that is known as an input node or a source node. Similarly, if you have a node will be called as an output node or a sink node only if it has only incoming branches. So if you see this node y4, so in y4 you see there is only one branch which is coming in, nothing is going out of this branch. So that means y4 will be considered as the output node. And apart from this input and the output node, this y2, y3, these two nodes, they have both incoming. There are signals which are coming into the node and there are signals which are going out of the node also. So those kind of nodes are known as mixed nodes. Okay, so y2 and y3 are mixed nodes over here. Now, what is a path? So path basically means the traversal of the connected branches in the direction of the branch arrows. Okay, such that no node is the path doesn't retrace back to that same node, so that no node is traversed more than once. Okay, so that means a path can be, so if you start from y1, so you start from y1, you move to y2, then y3, then y4. Okay, so this is one path you can say. And another path can be, so there can be like forward path. So forward path means the path from the input node to the output node. Okay, so here the forward path is you start from y1. So this is your input node and y4 is your output node. So that means the forward path will be you start from y1, y2, y3 and y4, right? And this will not be in the forward path because the direction of flow of the signal, it is in the opposite direction. So this will not consist, this path will not come into the picture of the forward path. Okay, so now if you have a loop, so what does a loop means? Loop means if a path originates and terminates at the same node, then it is called a loop. So let's say a path, it starts from y2, moves to y3 and then comes back to y2, and it follows exactly the direction of the branch arrows. So that means this is basically, it is completing one loop, and you can say that y2, y3 and again coming back to y2, this consists of one loop. Okay, then you can have non-touching loops. So non-touching loops basically means that loops which have no common node among each other. So if you have another loop over here, let's say it is connected again, there is some interconnection after y4, or so if there is a loop over there, so that means this loop y2, y3 and coming back to y2, this loop is not touching, or they do not have any common node among each other. So those kind of loops are known as non-touching loops. Fine. Then we have forward path gain. So forward path gain will be the product of the branch gains which are encountered in traversing a forward path. So here, first of all, when you found out what is the forward path, so it was y2, y3, sorry, y1, y2, y3 and y4. So that means if you want to find the forward path gain, it will be the product of all the gains of the branches which are there in the forward path. So that means A, B into C. So A, B, C will be the forward path gain. Now, if you want to find the loop gain, so you see what is the loop and then you multiply the branch gains that are encountered while traversing the loop. So that means here, so you have B and you have minus D over here. So then the loop gain will be equals to minus B into D. Okay. So now let's talk about some properties of signal flow graph. So signal flow graph basically it applies also for only for linear systems, and this equations. So the basic construction of signal flow graph is done from the basic describing equations of the system. So first of all, whenever you are given with a system, so the first thing that you need to do is that you have to write what is the expressions, or you have to write the equations which are governing the dynamics of the system. So once you have done that, so this equations on which the signal flow graphs are based, they should be algebraic equations and they should be in the form of like cause and effect kind of a relation. So there should be an input and there should be an output. So you have to represent the algebraic equations in such a way that it is in a cause effect kind of a relationship. Also, usually the nodes, they are generally arranged from left to right because obviously once the signal flows, the left side is basically your input and the right side is your output. So that means the signal is starting from the input and then going through all the different branches and blocks which are there in between, and then finally going to the output, and which is the effect. So your input is the cause and your output, which is that is the effect. And also the signals, they travel through branches only in the direction of the arrow which is provided. So if the arrow is provided from left to right, so that means the signal will always travel from left to right. And if the arrow is in the other direction, so that means the signal will move in the other direction. So now let's see how to draw a signal flow graph. Okay, so now let us say that you have been given with a set of algebraic equations. So you have y2 equals to some gain into y1 plus a, some gain into y4. So you have been given like five equations. Okay, so here you see that you have and there are 6 nodes. So y1, y2, y3, y4, y5, y6. So these are the 6 nodes that you have. Fine. So what you need to do here is that we have to find out, we have to draw the signal flow graph. So what we'll do first is that corresponding to each equation, we'll draw a graph, and then at the end we'll combine all the graphs together and find out what is the final signal flow graph. So for the first equation, so it is given that, so first of all, you have 6 nodes. So you represent 1, 2, 3, 4, 5, 6. 6 nodes are represented. Then what we will do is that depending on what equation is provided, you will connect the branches and denote the corresponding gains in those branches. So here you see that y2 is equals to a12 y1 plus a42 into y4. So that means y2 here, there will be one branch coming from connecting y1 and y2, and another branch connecting y4 and y2. So you have one branch over here, other branch over here. And then you see what are the gains. So the gain of the branch between y2 and y1 is a12, and between y4 and y2 is given by a42. So this is the signal flow graph for the first equation. Similarly, if you see the second equation, so second equation is we are trying to see what is the value at node y3. So y3, it has connections with y2 and y5. So we connect these two, and again correspondingly we write the corresponding gains. So here you see, since it is given A53 means the gain, or the like how do you find out what is the direction of this one. First of all is that it's a since we are finding the system variable or the variable at each node. So since there is an addition, means that both nodes or both the branches will be coming into that corresponding node. So that means this arrow will also be inside, this arrow will also be going inside. Otherwise, if it was like in the opposite direction, then the value of y3 would only have been given as a23 into y2, because we have already said that while finding out the node variable or the system variable at a particular node, we are only considering the number of incoming or inflowing signals. Okay, so now similarly for the third equation, you can write that between y3 and y4 the gain is a34, and so on, and you can finally, so you have 1 2 3 4 5 equations, or rather for 5 equations you have 5 individual signal flow graphs. Now what you need to do is that you have to combine all the signal flow graphs together in order to find out the overall signal flow graph. So while combining, you see that first of all these branches will be combined, and then you will combine this from y3 to y5, then from y5 to y3 there is something else, then from y4 to y2 there is a branch. So once you combine all these 5 individual graphs, you will end up with this. So this is the final signal flow graph which is representing this this set of equations. Okay, so once you have drawn this signal flow graph, then we'll see that there are different other what is that gain formula which we can use in order to find out what is the overall transfer function of the system. Okay, so now let's say that you have been given with these corresponding equations. Okay, and you have been said that y1 is your input and y5 is your output. So then can you help me construct the signal flow graph? So how many nodes are there in this particular, these 4 sets of equation?
Ma'am, 5 nodes.
5 nodes. So let me represent 1 2 3 4 5. So the nodes being y1, y2, y3, y4, y5. Okay, fine. So then what will be the corresponding to the first equation? So how many incoming branches are there for this y2? So what will be the connections, interconnections between different nodes? Like we are now, we want to find out what is the value of the variable at y2, that is given by a1 to y1 plus a3 to y3, a4 to y4, a5 to y5.
Ma'am, one straight connection, one forward path, and other all loops will get 3 loops and 1 forward.
One forward path as in from where to where?
Yes, y1 to y2, ma'am.
y1 to y2. Fine. What is the gain?
Ma'am, gain is a12.
A12. Then
we'll have a loop from y3 to y2, ma'am.
Loop as in, okay, fine. So something like this from y3 to y2. This is A32, right? Then
and we'll have from y4 to y2, ma'am.
y4 to y2. This is A42. Fine.
Then we'll have from y5 to y2, ma'am. A5.
Let us see something. This is A52. So this is for the first equation. For the second one,
ma'am, we'll have a straight forward path from y2 to y3, ma'am. A23.
y2 to y3. This is A23. Good. Then the second, the third.
Y3 to Y4 straight path, ma'am, with a gain A34. And ma'am, I didn't understand this Y4 equal to A4 for Y4, ma'am.
So this Y4 equals to A44 to Y4 means there is a path starting from Y4 and ending at Y4. Okay, so this will be, so there is a path which is starting from this node and then coming and ending at the same node. So usually we were considering as loops which were starting from one node and ending at a separate node. But this is also a loop, but the loop it starts from the same node and comes back to the same node, but just that the gain will be something else. So this is a gain of A44. Okay.
Yes, ma'am.
Okay, and then you have the last equation. So this is A45 and you have something coming from Y3 to Y5, that is A35. Now what you can do is that you can simply connect all these together and you will end up with the final Y4, Y5. So you have here Y2 to Y3 is A23. Here you have one other loop A44 and now you connect. So you have one over here. I don't think I'll get much space. A3B. Right, and what I have left off with this Y3 to Y5. There is another. This is A35. So here you will finally you will end up with the overall signal flow graph. Okay. So now let's see that what is the so once you have found out the signal flow graph, then what to do with that? So fine, we have drawn how the signal is flowing from the first node or the input node to the output node. But what will I do with this? So then what comes into picture is something which is known as Mason's gain formula. Okay, so using the Mason's gain formula, it says that the overall gain of the system, if that is given by T, so that will be equals to 1 by delta summation of Pk delta K. So now, so T is basically the overall gain of the system. Delta is known as, or rather Pk, P suffix K, that is given, that denotes the path gain of the kth forward path. So if your system has like multiple forward paths, then for each forward path, the gain of that forward path is given by Pk, and then delta is basically the determinant of the graph. So how do you find the determinant of the graph? So first of all, what we do is that we write, so the expression goes like this, that delta is equals to 1 minus summation, sum of all the loop gains of individual loops. So first of all, you figure out how many loops are there in your system, and what are the loop gains. So 1 minus summation of the loop gains of all individual loops plus summation of the gain products of all possible combinations of two non-touching loops. So two non-touching loops means, so non-touching loops, as in we have already told that if two loops do not have any common node, that is known as a non-touching loop. Right. So now if you have, like, let's say you have 2 or 3 non-touching loops. Now if there are 3 non-touching loops or rather there are 2 non-touching loops, so that means you have to find out the possible combinations. So let's say if you, or rather if you have 3 non-touching loops, so let's say you have one non-touching loop 1, one non-touching loop 2 and another is 3. So if you want to find out what is the possible combination of 2 non-touching loops, so one combination will be these 2 together, one will be these 2 together, one will be these. So there are like 3 possible combinations. So sum of the gain products of all the possible combinations of 2 non-touching loops minus sum of the gain products of all possible combinations of, if you have 3 non-touching loops, so on and so forth. You have to find out. In general, usually only till 2 non-touching loops are generally present in the systems. But in case if you have a system where, if you are given with a system which has more than which has 3 non-touching loops, then you have to include this term also. So this is, and the value of delta k, basically delta k is the cofactor of delta for the kth forward path, and this means kth forward path with the loops which are touching the kth forward path, they have been removed. Okay, so if you want to find out the value of delta k, so delta k will be 1 minus summation of gains of all the loops that are not touching the kth forward path. Okay, so that will give you the value of delta k. And PMR, basically PMR is while finding the value of this determinant, you will have to find PMR. So PMR basically is the gain product of the mth possible combination for R non-touching loops. So this, once you have, so basically what you need to find from a signal flow graph, you have to find out the value of delta, you have to find out the value of pk and delta k. So once you have found out all these values, you can use this formula and you can find out what is the overall transfer function or overall gain of the system. So this will be more clear if we do one example. So let's say that this is a signal flow graph which has been provided to you. Fine. So y1 is my input node and y6 is my output node. Okay, and what I want here is that I want to find the overall gain of the system. So y6 by y1, that is what output by input, that is what we try to find. So the first step is to find out how many forward paths are there. So how many forward paths are there in this system or in this signal flow graph?
5, ma'am.
No, forward path means the path starting from the input node and ending at output node. So this is one path, that is fine, but if you want to find out the forward path, means you have to find out the path which starts from the input and ends at the output, following the direction obviously which is there in each branch. So how many forward paths? So there are 2 forward paths. You see, there is one path which is moving along this direction, y1, y2, y3, y4, y5, y6. Correct? And then there is another path which is moving from y1, y2, y3, then straight away going to y5 and then y6. Right? So there are 2 forward paths. So one is y1, y2, y3, y4, y5, y6, and the other one is y1, y2, y3, y5 and y6. Am I right?
Yes, ma'am.
Okay. So now if you want to find out what is the, so this is forward path number 1, y1, y2, y3, y4, y5, y6. So what will be the gain of this forward path? So gain of the forward path will be some multiplication of all the gains of the branches which are traversed while you're moving along that path.
Ma'am, so it will be A, B, C, D, E here.
Yes, it will be A, B, C, D, E. Similarly, for the second forward path, what will be the gain?
Ma'am, A, B, E.
There is a G over here. Let me erase this thing. There is a gain over here also, no? So A, B, then you are encountering G, and then you are encountering E. So it will be A, B, G into E. Right?
Yes, ma'am.
Okay. So and now can you tell me what are how many individual loops are present? How many loops are there in this graph? Loops means it starts from one node and then comes back to the same node after following some other path.
Ma'am, two loops are there.
Only two loops. Okay, fine. Let me tell me what loops are there.
Ma'am, one is G and H, ma'am, because it's starting from the same path and ending at same path again. And second one is the F1, ma'am.
What about this one and this one? This is not a, these are not loops. This starting from Y2, Y3 and coming back here. Similarly, Y4, Y5 coming back to Y4.
Oh, yes, ma'am.
These
also loops.
Those two are also loops. So there is one loop over here which starts from Y2, Y3 and comes back to Y2. Then you have Y3 goes to Y5, comes back to Y3. Then you have this path, this loop, Y4, Y5, Y4. And then there is this another loop which starts from Y5 and again ends at Y5. Okay, so these are the four loops which are present in the system. Now, if you want to find out the loop gains, what will be the loop gains?
Ma'am, one more loop will be there, no, ma'am. Here, Y3, Y5, one is there. Again, it is returning, ma'am. G and H.
Yeah, that I wrote now. Y3, Y5, and Y3. So this will be G.
Loops will be there, no, ma'am. Here.
1, 2, 3, 4. Okay, another is this one, right? So another is Y3, Y4, Y5, and again Y3. So there will be 5 loops. So correspondingly, so for this first loop, it will be B into J. Then for the second loop, it is G into H. Then you have this, so this will be D into I. Then you have Y5, so this is F, and then this one. So C, D into H, C, D, and H. So you have 5 loops. Just hold on for 1 second. Hello.
Yes, ma'am.
Hello. Yeah, so what we'll do is that since it's almost end of the class, we'll continue discussing on this how to find out the overall gain of the system using this Mason's gain formula in the next class. So so do you have any doubts in today's class?
No, ma'am.
Okay, so then what you do is that you try to do the block diagram reduction, you try to practice the problems which I have already given. In case you are facing any difficulties, we can always discuss in the coming classes. Okay?
Yes.
So then, okay, then that's all from my side today. Thank you, and we'll meet again next week.
Thank you, ma'am.
Yeah, thanks. Bye.
Can you upload the first quiz solutions?
Yes, I'll do it by the weekend. I'll do it.
Yes, ma'am. Thank you.
I remember. Okay.